Hi. Okay, today we're going to be talking about one of the subtopics, sub-concepts in forces and dynamics, which is the scenario of terminal velocity. Okay, let me spell it out. Terminal velocity. Okay, so that's the main concept that we are going to be dealing with in this lesson. Okay, suppose you are on top of a very high-rise building. It is very high, and you're standing at the top of a building, and you release a ball, right? So initially, when you opened your palm, when you open your fingers, and the ball starts dropping, the very initial velocity that it has is 0 meters per second. U stands for initial velocity. Now, if you are not moving instantaneously at a point in moment, your initial speed is 0, then your air resistance would also be 0 newtons. Right? This is because air resistance, intuitively, it's directly proportional to velocity. Right? Because if you are not running, for example, then the air resistance that you experience it's going to be 0. Yeah, the faster you run, of course, you will feel more air. That's air molecules that's smashing into your face, so you will encounter a greater air resistance. Right? Just for some additional knowledge, now F air, right, it's actually directly proportional to velocity for low speeds, right? For low speeds, when you are dealing with high speeds, for example, a car that's racing very quickly through the road, it's actually a v squared. Now, v squared relationship, it's for high speeds. Okay, don't worry too much about this. If you are encountering this during an exam setting, they will have to tell you the relationship. Is it directly proportional to v, or is it directly proportional to v squared? Okay, regardless, in both scenarios, if your velocity is increasing, then your air resistance should rise as well. Right? Okay, this applies for the case of the v squared situation. Okay, let me redraw the diagram and illustrate again what's happening. So you have a ball that's falling. Very initially, the only force that's acting on the ball is its weight. Now, weight, you are familiar. It's equals to mass times acceleration due to gravity. Okay, so acceleration due to gravity, normally for a situation that's near to the surface of the Earth, as compared to its radius of the Earth, right? Usually we treat the value as 9.81 meters per second squared. If you want to approximate it to 10, in some situations it's fine. Okay, so very initially, your speed it's equals to 0. It's equals to 0, and your air resistance, subscript air, it's equals to 0 newtons as well. Now, as the ball starts to fall, right? As the ball starts to fall downwards, clearly the velocity is not 0, right? The weight is still there. Velocity, it's non-zero, and you will have therefore some degree of air resistance, right? So the air resistance will appear, and the net force as a result, now it's equals to weight minus F air, right? So as F net is equals to mass times acceleration, right, which you guys have learned before, Therefore, as my air resistance is rising, as the ball moves faster and faster, the air resistance is rising, right? And this causes the net force to fall. Right? Mathematically, you can see that if this is rising, therefore this is falling, and therefore the acceleration it's falling. The acceleration it's falling. And let me draw the diagram here in my final scenario that I would like to illustrate to you. Imagine that now as the air resistance grows, it grows so much until it's equal to the weight. So you notice that the vectors drawn for my weight as well as my air resistance is now equal in length. I'm trying to illustrate that the magnitudes are now the same. Therefore, in this scenario, F net, the net force acting on the object, it's equals to 0. Right? Because mg minus F air equals to 0. They are of the same magnitude. And this implies that acceleration is equals to 0. Right? Okay, let me summarize the situation. See, in scenario 1, F air, right? F air resistance is equals to 0. The net force is equals to the weight. Right? The body is therefore accelerating downwards. In my second diagram, as velocity increases, right? As velocity increases, my air resistance increases as well. But this causes my net force to fall. Right? And therefore, this means that my acceleration is falling as well. Now, in my final diagram, in my third scenario, my third picture, finally, my air resistance is increased until it's equals to my weight, and my net force is now 0, and my acceleration is now 0. If I were to plot a graph of velocity in meters per second versus time in seconds, what kind of graph do you think it looks like? Well, initially I have a certain I don't have air resistance, and that's because I start from 0 speed. However, my weight is causing me to accelerate, so I'm having a slope, right? So my velocity is increasing, but as air resistance increases, the slope will decrease, right? Because the gradient of my graph represents acceleration, right? So acceleration is decreasing, and finally the speed will be equals to a constant value. Reason being that acceleration is finally 0, as illustrated here. Since acceleration is 0, gradient of the graph is 0, and the velocity is now a constant value. This constant value of velocity, we call it the terminal velocity. Why terminal velocity? Simply because the value of the velocity terminates at a particular value here, right? And this is where my weight is equals to my air resistance. Well, that's all I have today. Next lesson will be coming up soon. Thank you.